Mathematics Radio. This is the final episode of 2019. Next week it'll be 2020, and we'll be back. Everyone will be back at school. We'll get started again. For the moment, if you got any math questions, feel free to tweet them to @NightMathRadio on Twitter, and I'll try to answer them here live on the air. For the moment, this is Nighttime Mathematics Radio. Coming to you live from our secret headquarters by the bay, bringing you math help and the worst loops Apple has to offer. I'm expecting this to be a quiet night, given that I think hardly anyone's at school on the weekend before New Year's, the weekend after the holidays. But if anyone is, or has a big math problem, and they just can't wait till next week to handle it, tweet on in and I'll be happy to help. For anyone who hasn't tuned in before, this is Nighttime Mathematics Radio. The way this works is you can tweet problems to me live on Twitter. I'll try to answer them here on the air. I can't guarantee your question will be answered, but I'll do the best I can. Alright, well, as expected, it's nice and quiet tonight. Hardly anyone's calling in. So let's take a look at a problem that seems sort of interesting. Dig around through our archives here. Let's take a look at an interesting problem here from the archives. Dig around for a moment, find a good problem to give. see. How about this one? Now, let's see. Actually, I'll come back in a few minutes with an interesting problem. For the moment, let's hold off for a moment. Fortunately, my archives are a little further away than I was hoping they'd be. For the moment, this is Nighttime Mathematics Radio. Once again, if you have any questions, feel free to ask them on Twitter, and I'll happily get to them on the air. This is Nighttime Mathematics Radio. Hello, everybody. If anybody's tuning in now for the first... Hello, everybody. If anyone's tuning in now for the first time, this is Nighttime Mathematics Radio. We take live math questions on Twitter, so you just have to tweet them to @NightMathRadio, and I'll try to get through them right here on the air. For the moment, let's look at a problem from, say, midway through differential calculus, just to have something from the archives. The problem looks like this. You're told to find the limit as x. Told to find this limit. Find the limit. Wow, my camera is very zoomed in today. That's maybe too zoomed in to use, but that's all right. Limit as x approaches 0 of 2 sine 5x over 3x. So if you look at that, the first thing you always try to do is say, well, what would happen if I just plugged x in? Because, of course, if you plug x in and you get a number, and it's a nice continuous function, which this looks like it is, except where it blows up, then this will work fine. So we plug it in, and you see we get 2 sine 0, which is 0, divided by 3 times 0, so this is a 0 over 0 indeterminate form. Now, we could wade into the limit itself, and that would work, but we've got better options. And the better option at this point in the course is you should remember something called L'Hopital's rule. The idea of L'Hopital's rule is, if you have an indeterminate for 0 over 0 form, and that's what we've got right here, then you could take the derivative of the top and the bottom of the fraction with respect to x, and then the limit of the ratio of the derivatives will be the limit if it exists. So let's try this. So that should be equal to, that's a 0 over 0 determinate form, so let's take the limit, that should be the same as limit as x approaches 0 of the derivative of the numerator Well, derivative of 2 sine 5x, that's just an easy chain rule problem, is 2 cosine 5x times the derivative of 5x, which is 5, divided by the derivative of 3x, which is just 3. So that's the limit as x approaches 0 of 10 cosine 5x over 3, and that's not an indeterminate form at all, because cosine of 0 is 1, so that's just equal to 10/3, which is the limit of that ratio. This is Nighttime Mathematics Radio. So once again, if anybody's got any burning math questions, feel free to tweet them to me at nightmathradio.com. I'll take a look at them here on the air. This is Nighttime Mathematics Radio. This is Nighttime Mathematics Radio. We're bringing you math help and the worst Apple tracks that we can find on GarageBand. Feel free to tweet them to me. Tweet any math questions you want to me here at Night Math Radio. I'll try to answer them live on the air. Howdy, everybody. Welcome back. This is Nighttime Mathematics Radio. If anybody has any math questions, feel free to tweet them at me on Twitter, and I'll try to answer them live on the air. For the moment, I got a question by other means, and it's a bit of a vague question, so I'll probably blather for a little bit about this one. But someone asked, what can you tell me about slope? I'm an Algebra 1 student. I'm trying to understand slope, and I just don't quite get what's going on. So let's talk about slopes. So let's take a look at slopes for a minute here. This is a good one. So everyone's first given the slope formula. They say, what is the slope formula? And they say the slope m is given by y2 minus y1 over x2 minus x1. And that's easy to write down. The question is, assuming you write little teeny numbers for the 2's and 1's, but what does that actually mean? What are we talking about here? And basically, this is something you use all the time in real life. This is a rate. To see where these come from, let's look at a problem you actually do all the time. You say, well, I drove 60 miles away, And it took me an hour and a half to get there. So you can sit there. So one question you start asking is, well, what speed was I going on average then? So, okay, in that case, what would the Y's be? The Y's are how far you are. The answer is, well, how do I know this? Because there's a key word here you can always remember. There's this word per. And what per means is divided by. So when we say miles per hour, we're literally talking about miles divided by hours. We're saying how many miles go by divided by how many hours. So if I said, well, we went 60 miles, so what this difference is how far were we at the end of the trip and how far we were at the beginning of the trip. The 2's are end, the 1's are beginning. Well, the end of the trip we were 60 miles away. The beginning of the trip we were 0 miles away, where we are. How long did it take? Well, it took an hour and a half. So at the end of the trip, it was 3/2 of an hour. Beginning of the trip was the start of the clock, so it was at 0 hours. So we could do this. This is just fraction division. This is 60 divided by 3/2, or 60 times 2/3. So that's 40 miles divided by hours. And the cool thing is units work exactly like numbers. So if there's miles in the numerator and hours in the denominator, then the unit of the whole thing is miles divided by hours, or miles per hour. So we were on average going 40 miles an hour. I know people don't think of that as a slope, because when you're first introduced slopes, you're introduced them very geometrically. You see them plotted always like this. You always see, well, here's my point x1, y1. Here's my point x2, y2. And so you're told, well, it's rise over run. So you sit there and say, well, how high up did you go divided by how far over did you go? And you say, well, this height, well, this is y2 minus y1, is this little height here. This run over here is, well, it's the end distance, x2 minus the initial one, x1. And so my slope is the slope formula. But in real life, you very rarely are using these geometrically. You can, but that's not usually when you see slopes. When you see slopes in real life, usually you're talking about rates. You're talking about miles per hour, because you want to know what average rate of speed you were going between your end point and your start point. Or you're talking about gallons per minute because you're trying to drain a bathtub and you're getting worried it's getting a little slow. Or you're talking about, well, any number of things. You're talking about inches per year because you're worried about, you're living in California and you notice that some of the train is moving relative to the rest of the train because we live in a geologically interesting area. That sort of thing is where is usually where you see slopes in real life. Really, in real life, slopes are rates. And that's really helpful, because that helps you understand what we're talking about when we write the formula of a line. We write the formula of a line, we typically write it in standard form. We write y is equal to slope times x plus the y-intercept. This is something that's called slope-intercept form. Why is it called that? Because those are the two numbers you could see. If I write down something like y is equal to 6x minus 3, the things I can just read off without having to do any math at all are the slope, which is 6, it's the thing multiplying x, and the y-intercept, which is minus 3, because it's the thing that isn't multiplying x. And that's all well and good, but again, geometry is not usually what you're thinking when you do a problem like this. Where do you really see these problems? You really see these problems if you say, well, I'm traveling and I'm going 60 miles an hour on average. I'm on some long empty freeway, so I can do 60. And I want to know how far I've gotten. And so you say then distance is equal to, say, my rate times time. And you see this all the time in, say, physics classes. And almost never do people just stop and point out, that's the equation of a line. This says your distance is equal to some rate times how long you've been going, or in other words, remember rates are slopes. It looks exactly the same as y is equal to mx. It's just it's a line with a 0 y-intercept. And why does it have a 0 y-intercept? Well, what the y-intercept really is in real life problems is the initial value. It's what is the function when you're first starting? Where do we start? And so for a lot of problems, you don't care where you start. If you're just saying, how far have I gone overall? The question, well, how far have I gone at time 0? The answer is nowhere. I've gone nowhere. So how do you express that? Well, you have a 0 y-intercept. But sometimes you do care. If you're emptying a bathtub, for example, you might say, well, I'm starting at 40 gallons. So I say the volume in my bathtub is equal to minus, say, 0.6, say, gallons per second times time. And now I really do need a y-intercept, or in this case, I guess a v-intercept. You need to know how many gallons did you start with. The answer is, well, you started with 40 gallons. You can write a similar one for your car. If you know the capacity of your fuel tank, if you've got like a 12-gallon fuel tank, for example, then the question of how much gas you have left is 12 gallons minus however many gallons per mile your car goes, for example. Suppose your car has, say, 22 miles per gallon, then that means it gets 1 over 22 gallons per mile times the distance you've traveled. And now you know how much fuel is in your car based on how far you've gone, assuming you're getting that 22 miles per gallon. Or, as they say, 1/22nd of a gallon per mile, which means exactly the same thing. So lines are absolutely everywhere when you're doing real-world problems. But people are sort of trained out of seeing them because they're so used to seeing y equals mx plus b that they don't notice how many lines show up in the real world. And they're absolutely everywhere. Because anytime you have a rate, anytime you say this is going at 60 gallons per mile, this is going at, well, that would be awful. That would be a rocket rather than a car. When you say, that when you say that you're getting 3 pages done an hour, that's of your homework set. Well, 3 pages per hour is a rate. So what you're saying when you say something like that is the number of pages you've completed is 3 pages per hour times the time you've been working. That's a line. Anytime you use the word per like that, or I'm getting this much done every this amount of time, you've actually written the equation of a line in English. That's why we study lines. It isn't because we're that suddenly very interested in geometry. And that's why this is such an important field. This is Nighttime Mathematics Radio. That was a fun question. Does anybody have any other questions coming up on Twitter? I'm going to wait about 5 more minutes to see if anyone comes up with any questions, and if not, I'll end the show. This is Nighttime Mathematics Radio. Thanks, everybody. Well, everybody, it's the middle of the holidays. Everyone's tired. Let's call it a night. Thanks, everybody. This has been a great 2019. Nighttime Mathematics Radio will be continuing into 2020. Keep tuning in Saturday nights at just after 10 p.m. and we'll stay on as long as I got questions. Or until 11 if it keeps going that long. This is Nighttime Mathematics Radio. Like and subscribe if you like the channel. And I'll see everybody next year. Good night, everybody.